Hello everyone. Before I start, I just want to say that if I do make a mistake or if you have any other questions, please leave a comment so that way we can answer those and help more students out. So today's problem is two rockets are flying in the same direction and are side by side. At the instant the retrorockets fire, rocket A has an initial velocity of 6,500 meters per second, while rocket B has an initial velocity of 8,700 meters per second. At that time, T, both rockets are again side by side. What is the displacement of each being zero? The displacement of each being zero. The acceleration of rocket A is negative 13 meters per second squared. What is the acceleration of rocket B? So this involves kinematic equations, and before I get into solving it, let me show you. These are the kinematic equations. I'm going to assume that you know what these are, and we will be using these equations for this problem. So this problem is a two-step problem. There are two parts to it, and we'll get into that. Another thing to note is there are two assumptions we are going to make with this problem. The first one being that we are going to ignore gravity, and the second assumption being that the acceleration is constant the entire time throughout the problem. So with all that said, I kind of already went down here and marked everything that we do know. We know that for rocket A in this column, the initial velocity is 6,500. I didn't put meters per second, but you should know the units. Meters per second, acceleration is negative 13 meters per second squared. And then the initial velocity for rocket B is 8,700 meters per second. And we don't know the acceleration. That's what we're trying to find. So just looking at this, we wouldn't be able to solve for use one of these equations because we need at least three of these variables covered. But we can use one of the principles in physics that we do know, and I can draw that out for you. So when a constant acceleration is provided, we know, so imagine this is a ball, right? It's being thrown up. These are at the same level, at the same height. After the peak right here, the ball's velocity going up will be the same velocity going down. It'll be negative, but it's the same number. And this is because there is a constant acceleration, which is gravity, and it is pushing it down. And so we can use this concept and use it with our rockets. So as right here's rocket A, as it's coming up and then it turns around, our rocket will have the same velocity at this point as it will at this point. And that's because there's a constant acceleration of negative 13 meters per second going down. Same thing with rocket B. We know that it goes up, there's a constant acceleration, and it is pulling it down. And within that time, this velocity will be the same as this, just going down. So when we write that, we can say that our ending velocity is negative 6,500 for A, and for B it is negative 8,700. And it's negative because it is going down in the down Y direction. Another thing that we know is that time is the same for both sides. Since time is the same for both sides, we can solve for that variable in column A, since we know three of these. And this is when our kinematic equations will start. So we know V naught, we know acceleration, and we know our final velocity. So just looking at that, we can go ahead and use our first kinematic equation. V is equal to V naught plus acceleration times time. And we can solve for time. So in part one of this problem, I'll go ahead and put a little one right here. Part one, we're going to go and use our kinematic equation. V is equal to V naught plus acceleration times time. And when we fill in all these values, we'll separate it from T first. So we're going to subtract, and we will end up with, this will become V minus V naught over acceleration is equal to T. So now that we have this, we can fill in everything, and we end up with negative 6,500 minus 6,500 over negative 13, and that is equal to our time. And then when we solve for that, we get 1,000. So our time is 1,000 seconds. I know it's seconds because this is in meters per second, and so when you take out the meters and you divide by the acceleration, once you put all the symbols together, you'll see that this is in seconds. So now we have our time, and like we said, our time is the same for both A and for B. And so now that we know time, we now have three variables that we can use to solve for rocket B. We know V0, we know the final velocity, and we know our time. And since we know those, we can use all three of them to solve for acceleration. So we're going to go back, and we're going to use our first kinematic equation, and we're going to solve for acceleration. So instead of isolating the t this time, we're going to isolate the a, so that way we can solve for it. So when we do that, when we use our first kinematic equation and we isolate for acceleration, we will get v minus v0 over t. And this will equal our acceleration. So now let's fill it in. So this now becomes we're using 8,700 here, not 6,500. All over 1,000 seconds. And we end up with negative 17.4. And this is our acceleration, so it is meters per second squared, and this is our acceleration for rocket B. I hope that made sense. If you need to rewatch it, or if you have any questions, go ahead and leave a comment, let me know. But if this did help, please leave a like, so that way other students know that this is accurate and we can help more students out. One thing I will say is when you are putting this into your calculator, make sure that you do subtraction first, so either put parentheses around it or input this and then divide by 1,000, just because of the order of operations. If you divide by 1,000 first, it'll skew it'll mess up the numbers. So, but there you go, and I hope this helped.